Chapter 16, slides 6 through 10. I wanted to do a short aside. Given that we just went through some of that orbital theory, I think it's kind of cool to think about that heat and light as a reagent, if you will, for these reactions to go. I thought we could demonstrate this by using the simplest ethene plus ethene system and thinking about how ethene plus ethene with heat or light could possibly form a cyclobutane ring. If you think about carbon 1, 2, 3, and 4. 1, 2, 3, and 4. Pericyclic reactions such as these, here are the new pi systems moving to form your sigma bonds. We're going to see some of this pericyclic movement in subsequent chapters as we look at mechanisms. So I wanted to show you this one in anticipation of those types of reactions, and also kind of a fun aside. So can you see how you could take two ethene compounds and push them together pericyclic wise to form cyclobutane? How might that occur? So let's model ethene as its HOMO, 2 electrons, right? There's only 2 pi electrons in the system anyway. This looks exactly like the ethene we modeled when we were doing the Diene-phile of the Diels-Alder. And the LUMO, unfilled. And then it reacts with another ethene molecule, same exact energies, right? Same exact orbital diagram. In phase, and the only other way to do it is out of phase. 2 pi electrons filled, so we've got a HOMO and a LUMO. So either way, you know, it could interact either way, because these are the HOMOs and these are the LUMOs. Okay, here's the problem. If these two need to stack, let's just take the HOMO of one and the LUMO of the other, okay? So let's stack them and see if it works to make new sigma bonds. The HOMO has them in phase, and the LUMO, is out of phase. So do you see that as they stack on top of each other, these are a match, but these are not. So this would be an example of not allowed. This reaction shouldn't work, okay? So just by heating it, you're not going to get this reaction to go. However, if you add lots of light, photon source, what happens is that the light will allow one of the electrons of 1, let's say, we just need to excite 1, will be excited to the LUMO. So now technically this is not the LUMO anymore. Okay, so if you add photon source to excite one of the electrons from the HOMO up to the next level, this is now the HOMO, the highest occupied molecular orbital, and this is still, for the other one, this is still the LUMO. And so these are very close in energy, so these two are going to interact. Now, with light, I have the LUMO for the one on the left, right? And I can align the HOMO after exciting. And again, it's just, you have to make sure that you can turn them all over the place to match. So now, as we look at combining these, we get our match. Okay? Now, cyclobutane is ring strained, and so if you remove the light, so with light, you get cyclobutane. If you remove the light, it possibly could reverse back to the less strained ethene starting materials. This is a very bare bones way to think about how this pericyclic reaction plays a role in things like transition lenses. Okay, the material that your transition lens, like if you wear those glasses, that darken when you go outside in the sunlight, well, what's happening is that you've got this molecule that makes up the lens. And then when you go out into sunlight, you're giving it photon energy. And that photon energy can excite an electron to the next energy level. And then orbitally allowing the reaction to occur, some sort of movement of electrons, so that the molecule changes shape, giving you a new molecule with new properties, i.e. dark, right? A dark color. And then when you remove the photon source, you actually bring everything back down to ground state, and it reverts, it's reversible reaction. It reverts back to its starting material property. Getting back to our Diels-Alder pericyclic reaction, we're going to dig a little deeper now and consider very methodically all of the things that we should be thinking about when we're trying to predict the products of a Diels-Alder reaction. There is a lot more to it. And so I've listed it out in the box here. The first thing that you should do whenever you're prompted to consider a Diels-Alder reaction and predict the products is to find your diene and your dienophile. That's the first thing you got to do. Okay? Identify and number the diene. So let's say I had this. Notice that I'm putting the electron donating group, methoxy. How do I know? Well, here's my diene. And I've got a group hanging off the diene. 1, 2, it doesn't matter where you start numbering. You just like to number the 1, 2, 3, 4. Anything that's not 1, 2, 3, 4 is just an appendage off of the diene. So the methoxy group is an appendage off the diene, and I can tell you that it's electron donating. Why? Because it has a lone pair. You could donate in, right? If you drew it out, you could also see that dipole-wise, it's donating from the oxygen towards the carbon 1. All right, so we've got our diene. Then you want to do the same for your dienophile. Let me draw a very common dienophile. Here's a pretty common dienophile. Let's label it 5 and 6. All we're doing is numbering the 6 carbons that is ultimately going to be part of the 6-membered ring. Right? I'm trying to identify the 1, 2, 3, 4, 5, 6. Everything off of one of these atoms is just an appendage. We'll fill those in later. Okay, and I know that the carbonyl is an electron withdrawing group. Right, it's pulling electron density away from the 5-6 system. I always think highlighting your diene and your dienophile helps you to see the groups as a group off of your diene or off of your dienophile, and it makes it easier to sort of define them as their inductive electron donating or withdrawing groups as they are. Okay, so that's the first step. I also give you a little note up here that I'm showing you the normal demand. Normal demand for Diels-Alder means the donating group is on the diene and the withdrawing group is on the dienophile. Inverse demand just means that you reverse them. There's still going to be demand because one is electron rich and one is electron poor, and it does totally work with them reversed. But the most typical and widely used and I guess easiest to see is the normal demand system. So we're going to be concentrating on normal demand. But if any of you guys were thinking, well, what if you could swap the donating and withdrawing groups? Wouldn't they still be rich and poor and react? And the answer is yes, absolutely. But just to simplify things, I'm going to focus on the normal demand. Okay, so now step 2. We want the diene to be in an S-cis configuration. What does that mean? It means that the sigma, right, the sigma bond between the 2 pi bonds of your diene need to be, right, there's rotation technically around here, technically. And so S trans is preferred. And that's how I have it right now, S trans. You see how the 2 double bonds are opposite to one another. So the sigma bond places the pi systems trans to one another. Sigma trans. However, for Diels-Alder to react, I need carbons 1 and 4 to be kind of on the same side, right? I've been drawing it like this. This is S-cis, or sigma, the sigma bond, right? The sigma bond is cis, placing the 2 pi systems on the same side so that 1 and 4 can react on the same side as one another. Now, S trans is preferred. There is a rotation. So if these are in equilibrium, right, if these are 2 conformations of the same molecule, it's going to prefer being in S trans. However, I need it to be in S-cis, the less preferred configuration, the higher energy configuration, if I want this Diels-Alder to react. I call this the Pac-Man, and that's why I've been using yellow. I need Pac-Man, right, in order to do this chemistry. So you need your diene in the Pac-Man configuration, or the S-cis configuration, if you want to do the Diels-Alder. I also call it Pac-Man for another reason, for a subsequent consideration that you're going to see in number 3, endo versus exo. So the Pac-Man model, right, is needed, but it's less preferred from an energy perspective. Just like trans is lower in energy than cis because of steric hindrance, it's the same thing, right? I mean, consider the 2 groups off of 1 and 4. These guys could get totally in the way. Even if you have hydrogens here, I mean, there's steric hindrance right there in the mouth. So yeah, that's not going to be preferred. But I need it to be that way in order for the reaction to go. Given this consideration, let's look at 2 different scenarios. Reaction 1 and reaction 2. Which reaction do you think is going to undergo a Diels-Alder reaction faster, more efficiently, better? Well, when I ask this one in class, a lot of people will say 1. And I ask, well, why did you choose 1? And they say, well, because in 2, you've got more steric hindrance with this CH2 of the ring. And I say, yeah, however, there's 2 things going on here. In 1, I've drawn it as the Pac-Man, right? However, I just showed you that it's not the preferred configuration, and it is free to rotate and become the S-trans configuration. So you want it to be in the yellow, you want it to be in the Pac-Man configuration, but it's going to prefer being in the S-trans configuration. So this is going to be more sluggish because you've always got to kind of wait for it to get into S-cis. And when it is, you hope that it reacts. 2 is actually the winner here, okay? 2 is going to react more effectively and more efficiently. One of the reasons is that you've got it locked in as a ring, so it can't rotate out. It's locked into S-cis. So if you guys ever go in lab and we make you do a Diels-Alder reaction and you got to get it done in the time frame of a teaching lab, yeah, we've probably given you a diene that's in a ring form. So it's locked into an S-cis and you don't have to come back the next day to check on your reaction 12 hours later. The other thing about it, if you think about it, is that that carbon not only locks it, but it's also a CH2, right? Methyls, ethyls, butyls, any alkyl group is considered to be an electron donating group. So if you notice in one, it doesn't have any appendage off of the diene. So there's no donating group. In both cases, you're using the same dienophile, which is withdrawing, but you don't have a donating group in reaction 1. So reaction 2 is going to be the winner effectively. You could actually run this reaction in lab within the 3-hour time frame given, because you've got it locked into S-cis and you have technically, it's albeit weak, a donating group off of your diene. Okay, let's do consideration number 3. When looking at a Diels-Alder reaction, we could have these appendages off. We're probably most likely going to have these appendages off of our diene and dienophile. How do they orient relative to one another? Well, what you're going to see is that the mouth of the diene, which I like to, as I say, call Pac-Man, I call it the mouth, wants to chomp on the appendage. That's my way of thinking about it. I'll explain why. But if you've got an appendage, like a carbonyl that's electron withdrawing, I've got it configured in the boat transition state down below here. Okay, so you can see the mouth of the diene. Here's the mouth. And here's the dienophile. Okay. Now, if you'll notice, the dienophile has a carbonyl off of it, this aldehyde. Now, if I'm just going to draw, I'm going to draw the dienophile for you so you can understand what so there's that aldehyde. And what it's showing you is that this carbon right here has a hydrogen and an aldehyde off of it. There are 2 orientations. I could have the aldehyde on the outside of the mouth, away from the mouth of the Pac-Man. That's called exo, outside. Or I could have the aldehyde endo. Right, so here's the electron withdrawing group. And what I'm stating as a general rule, and there's a reason for this, is that endo is typically the approach that is favored. When I show these to students, they go, yeah, but isn't an endo bad because, like, isn't there steric hindrance here? Yes, but we have to consider the shape of this aldehyde and the fact that when I add a withdrawing group to a dienophile, it tends to be a carbonyl. This is why the reverse electron demand, right, putting a donating group there. If I'm doing normal demand, that means I'm putting an electron withdrawing group off of the dienophile. In this case, I've used the carbonyl aldehyde. I could have had a ketone. I could have had an ester. You'll see that carbonyls tend to be the most widely used electron withdrawing group. So this is an electron withdrawing group, and it's a carbonyl, which is very typical. Now, carbonyls also have pi systems, right? So let me highlight. Let me show it to you orbitally here. Here's the Pac-Man mouth of the diene. Here's your dienophile. I'm representing the aldehyde as its own p orbital system right over here. And what you'll notice is that there's this secondary orbital effect going on. It's not a bond, it's just an interaction. It's like, oh, you know, when I get all upset about hydrogen bonding not really being a bond, but more of an interaction, that's exactly what secondary orbital overlap is. You know what primary orbital overlap is? A bond. This is primary orbital overlap, meaning they actually come together and make a bond. Secondary orbital overlap means their orbitals are aligned, they're in phase, they're interacting with one another, and that's a good thing, but it's not going to form a bond. So this is called secondary orbital overlap. It's an energy stabilizing interaction. This is a good thing. It's like pi stacking. If you go into inorganic chemistry, you talk about pi stacking, and that actually lowers the energy of the transition state. So if this reaction, you know, needs help getting things to get together, this does help. So the withdrawing group is not only helping with pulling out the electron density of the dienophile, it's also having this interaction with one of the back orbitals, lowering the energy of the transition state and helping the Diels-Alder reaction along. So this is a positive thing, okay? And so that means that the orientation of your system, if you have that other pi system as your electron withdrawing group, is going to favor endo. And people always ask me, oh, well, is endo always happening? No. You could have reverse in Diels-Alder demand. You could have a methyl group there instead, in which case, yes, steric hindrance will be a problem. You can't have a tetrahedral appendage doing secondary orbital overlap. You need to have another pi system. And like I said, I'm going to concentrate on normal demand Diels-Alder, in which case we're going to be dealing with electron withdrawing groups off of the dienophile. Those tend to be pi bonded carbonyls, and carbonyls are trigonal planar p orbital systems that can participate in secondary orbital overlap. What a mouthful. So for all intents and purposes, the ones that you're going to see with me are going to be normal demand. You're going to have a carbonyl off of the dienophile, as I said, and you will see secondary orbital overlap. So as a general rule, endo is preferred. Why does this matter? Well, the orientation, if you look, is going to have an effect on the stereochemistry, right? You could, if you were peering from the top, if you were looking at this ring from the top, you'd see that the aldehyde is wedged and the hydrogen's going away from you underneath in the back of the ring. But it's the opposite had it come in endo. So this is going to have an effect ultimately on the stereochemistry we draw in the final product at that center. Ugh, how did this become so complicated so quickly? I know. All right, number 4, regiochemistry. Here is, we're going to go through again, okay? Here's a reaction, and I've shown you 2 different outcomes, okay? Let's go through. Identify the diene and the dienophile. Let's take it step by step. All right, and we're going to number them. Here's the diene. Ooh, and I have it in the good configuration, right? Like it's locked in a ring. So I've already checked off my second one. I'm going to label this 1, 2, 3, and 4. My 1 looks like a methyl group. 1. Okay. Now I'm going to identify the dienophile. There it is with its electron withdrawing group appendage on it. And I'm going to label it 5 and 6. And if I was super lazy, I'm just going to label it like this. And what you'll notice is that if I push my electrons, you can see the 6-membered ring formed. 1, 2 with the methyl off of it, 3 with the new double bond between 2 and 3, 4, 5, and 6. 4 and 1 share a carbon bridge. That's still there. Okay, and then off of 6 is the ester. Okay, that's what I would draw as the product, right? But because I've got an appendage, I've got this methyl appendage and I have my ester appendage, why did I line them up the way I did? Well, I lined it up the way I did because that's the way it was drawn as the starting materials. Let's flip one. Let's do this. Here's my diene. I left this whole system the same. There's my dienophile. 1, 2, 3, 4, 5. I'll just keep the numbering the same, 5 and 6, but what's to say I couldn't have done it this way? Pushed the electrons. Doesn't matter. They're all cyclic. Just kind of doing some carbon accounting. 1, 2, 3, 4, 5, 6. There's my 6-membered ring. I'll number it. 1 to 2, 2 to 3 has a new double bond, to 4, to 6, to 5. Off of 6 is the ester. Off of 2 is the methyl. And 1 and 4 share the bridge. Okay, so I'm going to highlight. Right, and that's what I drew over on the side here. Okay, so really, there's 2 possible ways I could have done this. Which one is the one that I'm going to form? I don't really know. Oh no. All right, so we've got to figure out regiochemistry. That's what this problem is. And you'll notice that in the box, I also write electronic match. Now you guys know how to do this, all right? One of the things I like to look at is the fact that, remember back in the alkene chapter when we did pi acid-base chemistry, the pi bond can react with an H+, an acid. And you guys would put the hydrogen on one side, but what formed on the other? If you remember, it was a carbocation. And you guys told me, yeah, the hydrogen's going to go here and the carbocation's going to go there. And then I'd say, well, why? Why did you put the hydrogen there and the carbocation where you did? And you tell me, well, the carbocation is secondary here. You don't want to make it primary, right? You don't want that. So why is secondary better than primary? And I'm pulling at you guys to give me more, oh, it's more stable. Well, why is it more stable? Well, it's more stable because there are more alkyl groups around it, right? The more alkyl groups, the more donating groups, electron donating groups you have, the more it stabilizes the empty orbital. Okay, well, let's look at our diene. Look at that methyl group off of carbon 2. Now, carbon 2, would you argue that carbon 2, I know that you guys would give this to me. Carbon 2, if I were to do a reaction with the double bond between 1 and 2, carbon 2 is the best site for a carbocation. Would you agree? Because it's the only site where you could form a tertiary carbocation. None of the other atoms, 1, 2, 3, or 4, if the pi bond breaks, there's no way you're going to form a tertiary carbocation. So if that's the case, I'm going to redraw it up here. You are moving electrons, right? If you're going to move electrons, why don't you move them so that, I'll say the best carbocation position is going to be this one. the tertiary one. So I want to move electrons such that that is the carbon that would generate a partial positive. Why? It's the most substituted. It's got the donating group on it. It's the one that can be more stabilized. So because of conjugation, because we have resonance among all of this pi system, I can now identify the most stable positive position and then extrapolate out negative, positive, negative, positive. So these are my two positive positions. Let's do the same for the dienophile. We just said that we've got a very strong dipole with this withdrawing group. So if you were to draw a resonance contribution, you could say, all right, here is the dienophile. You could draw only one direction for resonance because of the oxygen. The oxygen is very electronegative, so there's only one resonance that we can draw. And it looks like this, with the O minus. Oops. I'll show this to you in a different way as well. Right? So by resonance, you can see the oxygen's negative and that is positive, the carbon way at the other end. Another way to look at it is to start at the more electronegative atom and then do alternating. We did this when we were doing MCPBA for epoxides. Okay, so you could do it by resonance, or you could say, well, I've got a very strong dipole. That puts the carbonyls are always partially negative, partially positive. We know the carbon of the carbonyl is an electrophilic site. We talked about that too. So by alternating, because there's conjugation, we can alternate negative, positive, negative, positive. Oops. I get to the same place. Okay. Take a look at the electronics. What's more positive? What's more negative? Blue to blue is positive to positive. That ain't gonna work, right? We want positives to negatives. So of the two situations, let's highlight, right? Carbon 2 and carbon 4 are the positive carbons. Carbon 5 and carbon of the carbonyl are the positive carbons. So if 5 and 1 react, it's going to be positive to negative. If 4 and 6 react, it's going to be positive to negative. So this is the preferred electronic configuration, which ultimately predicts the regioselectivity for this Diels-Alder reaction. Oh my goodness, there is a lot to figure out in here. All right. So here's a little practice for you guys. Here are two examples, and you guys can predict the products for them. I'm going to give you one more. Okay, so for the first one, you have to say which one you think will react more rapidly or efficiently. And in the second one, I want you to practice your regioselectivity for the reaction given.